In the previous two lectures, we worked on the motion of equation for forward motion of a vehicle in a fairly generic sense. That means general motions that's governed by the Newton's second law. That is applicable for both conventional ICE type of vehicles, but also any other hybrid or electrical vehicles. Now in this lecture and the lecture that follows, we're going to focus on the series hybrid powertrain mathematical model. That is issues particularly related to series hybrid electrical vehicles. Now I use this series hybrid electrical vehicle is purely because it is one of the most commonly used configuration for hybrid electric vehicle, but also it is very similar to other two types, the plug-in hybrid electric vehicle and pure electric vehicle. Okay, so configuration wise they are very similar. They are really sort of more representative of modern electrical vehicles. So we're going to use that as our special case to discuss for the powertrain. Now the diagram here shows the basic component of a series hybrid vehicle powertrain. Okay, so on the very left hand side, if you have an engine that burns the fuel, the engine drives a generator through a gear set with a gear ratio of kg. The generator generates electricity that's kind of rectified and then charges the battery, but also drives the electrical motor as well. And the electrical motor drives the wheels through another gear set with a gear ratio of k0, and then the final differentials that distribute the output from the gear set to the two wheels. Okay, typically that would involve the use of a differential. Let me just find my mouse. Gearbox that sends the traction effort or traction torque into the left and right wheels. Okay, and so it's the key components are here: the engine, the generator, the electrical motor, and the wheels, and the battery as well. But we also have two gear sets to consider. One is between the engine and generator, and the other is between the electrical motor and the wheels. Okay, so to understand the gears, how gear sets work, I'm going to do a little bit of revision on how a gear works. Okay, so you can see on the left top corner, this is a representative of gear set, and it's basically involves two sort kind of discs with T's on each of them. They will have different number of T's and different number of diameters of the two discs. Therefore, the two discs rotate at different speed, but they also transmit the torque as well, but scale up or scale down depends on the ratio between the two, or the difference between the number of T's on the smaller disc and the number of T's on the large disc. Okay, so the ratio is defined by a factor of k here. Now, when k is greater than 1, that means the left wheel rotates faster, but with a lower torque the right wheel will rotate slower but with a larger torque. But the power, the mechanical power, which is the rotational speed times torque, will be the same if we assume no losses of the gear set. Now, the losses of gear sets can be quite small in general, so we kind of sort of assume an ideal condition where the losses are negligible. So the speed relationship between the two speeds, say omega 1 is the rotational speed of the smaller wheel or the disc, omega 2 is the rotational speed of the large disc. Then the relationship omega 1 equals to K, the gear ratio, times omega 2. Now, relationship between the torque at the first wheel and second wheel is reversed to that of the relationship between this rotational velocity. So in this case, T2 equals to K times T1 as indicated in equation number 2. So if K is greater than 1, then omega 1 will be greater than omega 2, but T2 will be greater than T1. That's the torque on the smaller disk. The power equals to, on the one side, the P1, that's the power of the smaller disk, is omega 1 times T1. The power of the second disk, the mechanical power, is omega 2 equals to T2. Now, if you substitute equation 1 and 2 into equation 4, then omega 2 equals to omega 1 over K. T2 equals to K times T1. K in the denominator cancels that K out. So that will give you omega 1 times T1. So omega 2 times T2 is the same as omega 1 times T1. That's the power of this first disk. So the mechanical power on both sides will be the same. Okay, so that's kind of basic configuration required for any gear set. So bear that in mind. Now we can actually look at different conversions and work our way through from the generator all the way to the wheels. Okay, so I'm going backward a little bit. So I'm going to look at the motor and the wheel. The wheels first. Okay, because there's a gear ratio, we define this. Let's just go back there. We define that gear ratio as K0 between the electrical motor and the wheels. Therefore, you can have this relationship. Omega M indicates the rotational speed of the electrical motor. Omega W, that's the rotational speed of the wheel. Therefore, omega M equals to K0 times omega W as indicated in equation 1a. Torque is going the other way. Remember, their actual relationship is reversed. So therefore, the torque on the wheels equals to the gear ratio times torque of the motor. So that's equation number 1b. Mechanical power of both sides will be the same. Power of wheel, that's omega W times TW, equals to the power of the motor, that's the mechanical power of the motor, that's the output of the motor. Therefore, I put a Mach there, or sometimes I use the subscript to indicate this is the mechanical power of the motor. Remember, the motor, both sides, motor in the motoring mode, when it's driving the wheels, the input is a voltage and current. therefore that's electrical power. The output will be torque and the velocity, which is mechanical power. Okay, so there's a difference there, but for time being, we are considering the mechanical power of the motor at the moment. Okay, so that's equation number 1C, and that's power of the wheel equals to power of the mechanical power of the motor. So that's between the motor speed and rotational speed. Now the wheels are used to drive the car or the vehicle. Therefore, there is also a defined relationship between the forward speed of the vehicle and the rotational speed of the wheel, depending on the size of the tire. So we use R to represent the radius of the tire. The relationships between the tire and the forward speed is such as defined in equation 2. V is the forward speed of the vehicle. Omega W is the rotational velocity or rotational speed of the wheel. R is the radius of the wheel. So V equals to R times omega W as indicated in equation 2. And force, the traction force, comes from the wheels. Okay? It comes from the torque delivered through the gear set from the motor to the wheels. So if the torque of the wheels or the total torque of the two equals to TW, then divide that TW by the radians, give you the traction force. Okay, that's the total traction effort required to drive the car forward. The traction FTR would be positive in accelerating mode when the engine motor drives the vehicle. FTR will be negative if you brake, whether through the motor in a reversed working mode or through additional mechanical braking discs. Okay, that's to slow the vehicle down. But FTR equals to TW over the radians. That's equation 3A. Or TW equals to R times the traction effort. So that relationship is the same. Basically just changes format slightly. So equation 3B and 3A are basically the same thing. But also, the power of the vehicle, the forward power, equals to F, the traction force, times the forward velocity. If you substitute the relationship equation number 3A and equation number 2 into there, we end up with TW times omega W, which is power of the wheel. So the power of the vehicle or power consumed for driving the vehicle is the same as the power of the wheels. We are ignoring small losses there. Okay, so these are the equations from equation 2 to equation 4 that define the relationship between forward motion and rotational motion of the wheels. Equation number 1A to 1C that defines the relationship between the motor and the wheels. Okay, so that's motor, wheels, and forward motion. Now, of course, if you look at the configuration of the series hybrid powertrain, we also have a gear set between the engine and the generator as well. Now, sometimes, depends on the actual design of the engine and the generator, sometimes that kg is greater than 1, that means to slow down. Sometimes kb can be smaller than 1, that means the speed of the generator is faster than the engine. That's all depends on individual particular engine and the generators. Okay, generators work to give you the best efficiency at its designed frequency range or the speed range. The engine will also have its required speed range in order to achieve the best efficiency. Okay, so kg is designed to match the two to give both the best efficiency. Okay, therefore the torque, because of that gear set, the torque at the generator side or the mechanical side, well, because the input to the generator is the motion, the mechanical motion, the torque and the rotation. That's because it's driven by the engine. The output of the generator will be electrical power. So the input side, you will have a torque, which is equal to kg, the gear ratio, times the torque output from the engine. And relationship between the rotational velocity of the engine and the rotational velocity of the generator is in a reverse relationship. So omega E equals to kg times omega g. Okay, so these two, just like all the other gear sets. Okay, torque is output torque equals to kg times input torque. Input velocity equals to kg times output velocity, or output velocity equals to input velocity divided by the gear ratio. So that's defining equation 1 and 2. And the output power of the engine, which is mechanical, equals to the power of the mechanical power of the generator, which is the input to the generator. So that's PE equals to TE times omega E. PG, mechanical, equals to TG times omega G. Now substitute these two into that equation, you can actually prove the output mechanical power of the engine equals to the input mechanical power of the generator. That's equation 1, 2, and 3 for you. Okay, so that's the relationship between the engine and the generator. If we consider the efficiency of the engine, the efficiency of the generator, the efficiency of the electrical motor as well, then we need to work out the relationship between input and output of each of the components by considering the losses in the system as well. And that, some of it we already derived earlier. So for example, for the engine, output is a mechanical, which is TE times omega E. For the generator, the mechanical power equals to TG times omega G, which is also the same as the mechanical power of the engine. For the motor, the mechanical power equals to TW omega M. For the wheels, the mechanical power equals to TW times omega W, which is the same as Tm, the torque of the motor, and torque of the rotational velocity of the motor, which is the product of the two will give you the mechanical power of the motor. Okay, so that's really just to reinforce the message here. The output of power of the engine, which is mechanical, will equal to the input power of the generator, which is also mechanical. The output of the output power of the electrical motor, which is mechanical, equals to the input power of the wheel, okay, which is also mechanical, and these two are the same. If we consider efficiencies, then we have these relationships. This just summarizes the relationship between the input and output of the system or subsystems. For the engine, mechanical power equals to Te times omega E. Now, if the engine has an efficiency of eta E, which efficiency, of course, is less than 1, so the input power to the engine is chemical power. It's come from petrol, burning the petrol. Okay, so that would be the mechanical power divided by that coefficient. Okay, or efficiency coefficient, or sometimes we call it the efficient constant. Okay, typically the efficiency of an engine is quite low. It's in the sort of 20%, 30% region. Or mechanical power of the engine equals to the chemical power times that. So the output would be much lower. The output power of the engine would be much lower. For the generator, the input is a mechanical power, which is Tg times omega g. But because of losses, the output, which is the electrical power, because generator generates electricity. Okay, so it would be the mechanical power of the generator times the eta g, which is the efficiency of the generator. Now this efficiency tends to be quite high, okay, in the high 90s, 95, 90%, above 90% is quite common. The motor, however, have two different modes. When you are driving, the mechanical power is output, that's TW times omega W. And input is voltage and current. But that can be divided by the mechanical power by the efficiency of the motor. That's eta m. That's again, this number can be quite high in the 90s%. On the other hand, if you're braking using the motor to brake it, because the motor can work in a reversed order to work in a way like a generator, in which case the power will come from the wheels and try to slow the motor down. This torque and the velocity of the motor generates electricity that is in turn going to charge the battery. So in this case, the input will be Tm times omega m. The output will be electrical, which is the mechanical times eta m, which is efficiency of the motor as well. So make sure that we are clear about these relationships. Okay, it's the power of the engine output with a efficiency factor, that's eta E. Okay, remember, whatever happens, output will always be less than input. Okay, so we actually have to rely on the values we know to work out. If we know the output power, then we can work out the input power. If we know the input power, we can work out output power, considering the efficiency factor. But always the output will be less than the input, whatever your calculations are. Okay, and so bear all these in mind. If you calculate something, you end up with output greater than input, then you got the efficiency factor wrong. Okay, because sometimes it's divide, sometimes it's multiply. So that is a summary of the power relationships. Okay. But also, if you look at this diagram there, the output of the generator is charging the battery and also supplies the electrical motor as well. So the difference between the two, because the generator needs to charge the battery, but also supply the energy to the electrical motor. So total energy equals to this energy, the motor energy, plus the battery energy. Therefore, the energy of the battery will be equal to energy of the generator minus the energy of the electrical motor. So that's what this equation is. So battery equals to Pg electric minus electrical power of the motor. Now if the power of the battery is negative, it can happen, which means electrical motor is drawing more energy from the system than the generator can provide. Therefore, battery is acting as a buffer to provide the difference. If the PB is positive, that means motor is drawing less energy or less power from the system than the generator produces. Therefore, the rest of the difference is used to charge the battery. Okay? PG cannot be negative because PG is how much energy is produced from the generator that is driven by the engine. But the motor power can be negative. Motor power is positive when it's in driving mode, when you drive the vehicle forward. But negative if the motor is working in a braking mode. Okay? And also, what you should notice is the power losses of battery are relatively small, so we can actually neglect as well. Comparatively, okay, there are losses, but compared with other losses, it's quite small. Okay, so that's power of input and output power of each of the components. We can also work out the overall power as well, or overall efficiency of the system. Now, I copied all the equations down from previous pages. So the battery power equals to electrical power of the generator minus electrical power of the motor. That's the equation number 1. Electrical power of the motor therefore equals to electrical power generator minus PB. And then I'm going to put what I'm done here is to say, right, because I know mechanical power of the motor is the same as mechanical power of the wheels, which is the same as the electrical power of the motor times the motor efficiency factor. Okay, so this in the bracket is what's in the equation 2. That's electrical power of the motor times the efficiency factor. That will give me the mechanical power, because this is less than 1. Now we are talking about driving mode or motoring mode. Okay, and therefore we get also, if you look at this, PG, the electrical power of the generator, can be converted into the mechanical power of the generator. There's something not quite right there. I think this should be divided by. No, can't be right. Should be divided by the. Let me just have a look. No, it is correct. Sorry. Electrical power is the output of the generator, which is which should equal to the input power of the generator, which is mechanical, times the efficiency factor. And that further, because I can replace that as well, because input power of the generator equals to output power of the engine. Now, then output of the engine, the output power of the engine equals to input power of the engine, which is PE chemical, times the coefficient factor of the engine. So I can just get that, these two terms together, replace that. Okay. Now, the overall efficiency of the system equals to total output power divided by total input power. Now, total output power is PW, mechanical. Total input power is PE, chemical. That's engine input. And the top is the output of the wheels, or output power of the wheels. Now, combine all this together, and you end up with equation number 7, which gives you the overall efficiency at any time. Okay, so that equals to efficiency factor of the generator times the efficiency factor of the engine, and times again the efficiency factor of the motor. Inside the bracket is 1 minus, on the top is efficiency factor of the motor times the power of the battery divided by P naught. P naught is the total output power, which is the mechanical power of the wheel, or the mechanical power of the vehicle, V times force, plus eta M, that's the efficiency of the motor, times power of the battery. Okay, so a lot of equations here, but just make sure that we understand what each of the equations are and how to use them. I'm going to use some of it in an example in the next lecture, but I will also set some practical questions for you as well. Okay, thank you.